thought I'd start to talk a little bit about how they work. This is the schematic of the orange squeezer. And I'm just going to explain a little bit how the thing works and then show you just some voltages, and then we will play some music through it so you get results. Let me start on this end over here. For those that are in 302, we're just about to have the lecture that describes how this thing works here. And then the lecture we just had explained how this works. But what this is doing, it's creating a constant current. And that current's going to flow into this resistor here. And so as you vary this resistor, you can change the voltage. So I've set this so this is at about 2.5 volts. Right, and then I'll explain where this voltage is coming from, but suppose that it's 1.25 volts. Then the difference is a negative 1.25 volts. This field effect transistor, when you change the voltage across its gate source, makes a varying resistor. And the resistor is kind of low up here. It gets higher and higher down here. So over here it's on maybe a couple hundred K. Up here it's 130 ohms. So as I change the voltage across it, as the voltage across it gets more negative, you can see little numbers here, the resistance goes up. Okay? So just got to keep that in mind as you go through this. So here I've got a negative voltage across here, and this creates a resistance here. When you look at an AC circuit, these capacitors that are here, when the frequency is high enough, they become basically short circuits. And so in the audio range, this is a short circuit, this is a short circuit, and actually so is this one here. And so what I've got is a resistor here, and another resistor really back to ground, and it's forming a, we call a voltage divider for those that are in 201 or 202. And the value of this resistance is about 14,000 ohms. Also for AC, batteries look like dead shorts. So there's also a short here, and this short's back to ground, and I get some resistors in parallel with this, but they're much bigger. So it's mostly dominated by this field effects transistor being turned into a 14K resistor. And what that's going to do for a 1 volt peak-to-peak AC signal is make the voltage here 14K divided by 14K plus 82K. That'll give you about 0.143 volts peak-to-peak. Then what's here is a non-inverting amplifier, 201 or 202 and or other classes. And again, this is a short in the audio band, so the gain is 1 plus the resistor ratio, which is 22, plus 1 or 23. So 23 times that shows up here. This looks like a short at audio frequencies, and I get out about 3.3 volts peak to peak. Now, this circuit over here is what's called a diode or rectifier, and what it takes is that it chops off the bottom of the waveform. So if I had a sine wave here that's going up and down, it's going to chop off the bottom of it, and that's what's going to show up here if this capacitor wasn't here. But the capacitor is going to hold that voltage once it gets to its peak. So the voltage here is really the peak of the voltage that was here, minus the drop across the diode. And this is a germanium diode. The drop's about 0.4 of a volt. So if you take this and divide it by 2, 1.65, minus this voltage is about 0.4 volts. And the reason they're using a germanium diode here is that the voltage levels are kind of low, and a silicon diode would be closer to 0.7. So what shows up here is we call a half-wave rectified waveform and smooth out. That's where I'm getting that voltage to come back here and create this resistance. Okay? Now, if I were to increase this voltage, maybe make it 2 volts, then the difference between this and this would be a negative half a volt. Now, this needs to have a negative voltage across it to work. That's really what these numbers were saying from here. I don't think you can read these, but these are all negative voltages. The more negative you are, the higher the resistance. So if I were to increase this voltage, say again, suppose that this is 2 volts, then I got 2 minus 2.5, and so I've got half a volt negative. So the resistance would actually go down in value. So it might go from 14K maybe to 5K or 10K. And that's going to make the voltage divider here lower. That's going to make this signal smaller. So that's how this voltage is impacting the resistance here. Okay, suppose that I now play a note on the guitar, or actually I wouldn't do that, Alan would. And I get maybe a 1 volt peak-to-peak tone, which has got a lot of sine waves in it. But now it's starting to decay. So suppose that it drops in half. So the voltage here then would drop in half initially, and the voltage here would drop in half. It's a linear circuit, everything's pretty much the same scale factor. That would make this DC voltage lower. Okay. That would then put a voltage here, maybe say it's 1 volt now. So 1 volt minus 2.5 is going to be minus 1.5 volts. So it's more negative than it was before here. And that's going to make the resistance go higher in value. And what that's going to do is make this maybe go to 20K. And now the voltage divider is not as low. So in other words, I'd have 20K here over 20K plus 82K. It's actually going to make this voltage want to go up in value. And that's going to keep this voltage here closer to what it was before. And it actually runs through a transient analysis till eventually it makes this 3.28 in steady state. And what's happening then is that this voltage is a little bit smaller, and that changed this resistance a little bit to kind of hold this fairly constant. So as something's changing here, this is going to readjust itself to eventually make this come back close to the same value as here. What's happening is the difference is being dropped across this 82K resistor. And so what you're getting is a constant output until eventually this really decays enough or a lot to where this can't sustain the feedback loop. And I adjusted this so that was about 100 millivolts here when we play this. So when whatever he plays drops to about 100 millivolts peak to peak, there's not enough voltage for this whole thing to keep working, and you literally have this constant volume just stop. You play a note, you'd hear it normally decaying down, but now it's going to play it for a longer amount of time. And with this pot, you can set where this is going to be. So this is at full volume on the pot here, you actually would get this, and then this volume control here just takes this and divides it down with a voltage divider. So that's how it works. So it takes a signal in, amplifies it, halfway rectifies it, use that to feedback and vary a resistor to ultimately, if this tries to go down, it tries to decrease it back up again. These are called constant amplitude circuits in electronics. It's a very common circuit we use in radios. You have a signal that's changing constantly that you're receiving with the antenna. And so in those radio circuits, they have a loop that just varies the gain to keep the output where you set it constant. That's what we're doing right here. We set this at a fraction of this or the full value, and this is going to regulate itself to keep that as it's changing to just one value. But eventually that string that's moving over a magnet is not going to be wiggling enough anymore, and the thing just dies. Okay. The pedal's not on, and what I've got is the input is on the top and the output's on the bottom. So if I vary this, they both go up by the same factor. You can see that right there. Okay, now I'm going to click the pedal on. I can adjust the output wherever I want to. But now if I increase the input, the output doesn't change. And then you can change the frequency. Turn this a little bit. See, as I was increasing and decreasing, it moved a little bit. What's happening is you're maybe getting, I would say probably less than 1 or 2% change here for a huge change on the other side. And so it's holding that value as long as this is being applied. So that's how that works. So a bunch of feedback loops, it's actually regulating itself, keeping the sound constant at the output. Well, let's hook a guitar up and see what this sounds like, and then we can get all this to work on here. So this is when it off.
You can hear it sort of a
decaying.
Turn on. Just keeps going. When I play that, I don't have a compressor, but when I play this little part right here, it's really quiet compared to the rest of the song. And I always have trouble keeping the volume up there. With the compressor pedal, it'll hold the volume up, so I don't really need to worry about my fingers getting in the way there. So when you barely hit a note, that's pretty much when it really comes in handy if you're close to missing one. Distortion, but hammer-ons also. Like if you barely hit it, you can still hear it with the compressor, as opposed to, without it, it really comes in way softer. So if you're playing something that involves a lot of hammering or pulling off, it's pretty good for that too. Those notes like I was doing earlier, I just sort of get it with my hand or something like that. I just accidentally mute it a little bit and it gets really quiet. With the compressor on, you won't notice, which is pretty handy if you screw up often.
Yeah, it's one of the pedals that people were building this semester. There's a lot more coming, and just kind of do this as we finish them. So, anyway, thanks for coming, and see you next week.